So we have the beginning of advanced classical mechanics practice final exam. This will be 15 total problems, and this is at first year doctoral level. So we're starting off this video as problem number 1. So number 1, a bead of mass m moves without friction on a circular hoop of radius r. The hoop lies in a vertical plane and rotates about its vertical diameter with prescribed angular speed. That's capital omega of t. Sorry about my poorly drawn omegas. Let theta be the angle of the bead from the downward vertical. So there's 4 components to this. So part A, choose a generalized coordinate and derive the Lagrangian. Part B, derive the equation of motion from Hamilton's principle. Part C, determine whether energy is conserved when capital omega is constant and when capital omega of t is time dependent. And part D, find the equilibrium points for constant omega and determine their stability. So we're going to go over the whole thing. So this is a Hamilton's principle with a moving constraint for a bead on a rotating vertical hoop. So let's begin here. A bead moves on a hoop of radius r. We're going to use theta measured from the downward vertical. And the bead position may be written as x equals r sine theta cosine capital phi of t, and y equals r sine theta sine of capital phi of t. Z is going to equal negative r cosine theta. And that's going to be where capital phi dot of t equals capital omega of t. So the speed here is going to be equal to v squared. That's equal to r squared theta dot squared plus r squared omega of t squared sine squared theta. So our capital T is 1/2 m r squared theta dot squared plus 1/2 m r squared omega of t squared sine squared theta. And taking the gravitational potential as v equals negative mg r cosine theta. From there, we're going to get the Lagrangian. The Lagrangian is L is 1/2 m r squared theta dot squared plus 1/2 m r squared omega of t squared sine squared theta plus mg r cosine theta. And the Euler-Lagrange equation gives d dt m r squared theta dot minus the quantity m r squared omega of t squared sine of theta cosine theta minus mgr sine of theta, and that equals 0. So m r squared theta double dot equals m r squared omega of t squared sine theta cosine theta minus mgr sine theta. Now, building on that, what we could say is for the equation of motion, so the equation of motion, theta double dot equals omega of t squared sine theta cosine theta minus g over r sine theta. And if omega is constant, the Lagrangian has no explicit time dependence. So the conserved energy is going to be E equals theta dot, this partial derivative L with respect to theta dot minus L. So E is going to equal 1/2 m r squared theta dot squared minus 1/2 m r squared omega squared sine squared theta, and then minus mgr cosine theta. And so from there, E is going to equal 1/2 m r squared theta dot squared plus v sub EFF of theta, where v sub EFF of theta equals negative 1/2 m r squared omega squared sine squared theta minus mgr cosine theta. And if omega equals omega of t, the Lagrangian depends explicitly on time. So energy is generally not conserved. that situation. Our equilibrium points here, they satisfy sine of omega squared cosine theta minus g of r equal to 0. So sine of theta equals 0 gives 0 and pi. And also cosine of theta is going to give us g over r omega squared. And this exists only if omega squared is greater than or equal to g over r. So the equilibria are theta equals 0, theta equals pi, and cosine of theta equals g over r omega squared if omega squared is greater than or equal to g over r. So stability follows from v sub EFF double prime of theta. And since v sub EFF prime of theta equals mr sine of theta times this g minus r omega squared cosine theta, then we could say this v sub EFF double prime of theta equals mr bracket g cosine theta minus r omega squared and times this cosine squared minus sine squared, close bracket. And at theta, that equals 0, and v sub EFF double prime of 0 equals mr times the quantity g minus r omega squared. And building on that, we have the following. We have, so theta equals 0 is stable if omega squared is less than g over r, and unstable if omega squared is greater than g over r. And now at theta equals pi, v sub EFF double prime of pi equals negative mr times the quantity g plus r omega squared, and that's less than 0. So theta equals pi is always unstable. And for the non-trivial equilibria, cosine theta equals g over r omega squared. At these points, one finds v sub EFF double prime of theta equals the following: mr squared, omega squared, sine squared of theta, and that is greater than 0. So the off-bottom equilibria are stable whenever they exist, and cosine of theta equals g over r omega squared is stable for omega squared being greater than g over r. Okay, so that's all for problem number 1. Thank you very much and have a great day.